Okay, now we're moving on to some polynomial equations. And in these, our strategy is going to be to factor, 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 and then use the zero product property in order to solve them. So we're kind of killing two birds with one stone here. We're going to practice our factoring skills and solving polynomial equations at the same time. So here we go. Let's see, what kind of a polynomial do we have? We've got a quadratic whose leading coefficient is 1. That means I think we can factor this polynomial as x plus some number, x plus another number. These two numbers are going to have to multiply to give negative 27, and they're going to have to add to give 6. So I'm thinking that this is going to factor as x plus 9 times x minus 3. You could multiply those together to confirm. And my claim is that if this guy multiplied by this guy is equal to 0, then it must be the case that x plus 9 has to be 0, or it must be the case that x minus 3 has to be 0. In which case our solutions are 3 and negative 9. I'm going to go ahead and check our answers on this one, but I'm not going to do them for all of them because it might just take too long. But you always can, and it's a really good idea if you have time to spare. So let's see, if x were equal to 3, let's see, 3 squared is 9, plus 18 is 27, minus 27 is 0. Amazing. Negative 9 quantity squared is 81. And then 6 times negative 9 is negative 54. 81 minus 54 is 27, minus 27 is 0. Amazing. They both work. All right, making moves. Okay, here, number 12. Ooh, we've got a trinomial. The leading coefficient is not 1. It's definitely not a perfect square. Ugh, we gotta do the AC method. All right, so here we go. 12 times negative 3 is negative 36, and negative 36 is kind of our magic number here. So we're going to find two factors of negative 36 that are going to somehow add to negative 5. So let's run through them. Let's see, 1 and 36, yeah, that's not going to be helpful. 2 and 18, yeah, no dice. 3 and 12, 4 and 9. All right, 4 and 9, we can make this work. So let's rewrite this original polynomial as, let's see, 12g squared plus 4g minus 9g minus 3 equals 0. And I think that now we should be able to factor this guy by grouping. So I'm going to group our first two terms, 12g squared plus 4g. I'm going to group our second two terms, negative 9g minus 3. Okay, always remembering that equals 0 at the end. So easy to forget about it. In our first grouping, I think we've got a common factor of 4g. So 4g times the quantity of 3g plus 1. In our second grouping, I think we've got the common factor of negative 3 times 3g plus 1. Awesome. These two guys are exactly the same, meaning we are ready to do this final step of factorization. So the final factorization is 4g minus 3 times the quantity of 3g plus 1. And my claim is that if these two guys multiplied by one another are equal to 0, then either the first grouping must be equal to 0, so it must be the case that 4g minus 3 is equal to 0, in which case 4g is equal to 3 and g is equal to 3/4. Or it must be the case that 3g plus 1 is equal to 0, right? At least one of them has to be equal to 0, in which case 3g is equal to negative 1 and g is equal to negative 1/3. So negative 1/3 and 3/4 are the two solutions to this polynomial equation, and I leave it to you to go ahead and substitute them in and confirm. All right, we're making moves. All right. Okay, so, one thing to keep in mind is once we see that this is a polynomial equation, we know we're going to have to factor, but we also know that one side of our equation is going to have a 0. That zero product property works with, well, only 0. So the first thing I would do here is add 1 to both sides of this equation so that we have a polynomial on one side and 0 on the other. So now let's try to factor this guy. It's a trinomial again. Again, our leading coefficient is not 1, but when I look at 9x squared and 1, I'm thinking this guy might actually be a perfect square trinomial. And you know what? It is. That is 3x plus 1 squared, or 3x plus 1 times 3x plus 1. And so, actually very similar to the last one, if this guy times itself is equal to 0, well, the only number that multiplies by itself to give 0 is 0. So it must be the case that 3x plus 1 is equal to 0. It must be that 3x is equal to negative 1, or that x is equal to negative 1/3. So this polynomial equation right here has only one solution, namely negative 1/3. Okay, got a couple more. All right, again, I'm noticing that we have on one side of the equation not 0, so let's go ahead and subtract that 25 so that we do have a 0 on one side of the equation. I'm also going to rewrite the left-hand side in standard form, because that's always a good idea to put our polynomial in standard form before we try to factor it. So we got negative 5a squared minus 30a minus 25 all equals 0. Yowza. All right, and before we do anything else, always want to look for common factors. I should have mentioned that earlier with the other examples, but they didn't have any common factors, so it's kind of a moot point. But here, I definitely see a common factor. I see a common factor of 5 amongst all three terms. I'm actually going to even factor out a negative 5, because it's always nice to have our leading term be a nice positive number. So I'm going to rewrite this as negative 5 times the quantity of a squared plus 6a plus 5. Again, equaling 0. And now we say, well, how does this guy right here factor? And I see a trinomial. The leading coefficient is 1. I'm feeling good. I think this guy is going to factor as a plus 5 times the quantity of a plus 1. You can multiply it out to confirm. And if these three things are going to multiply to give 0, at least one is going to have to equal 0. Now, negative 5 is negative 5. It's never going to be 0. So at this point, we can kind of disregard it a little bit. But with the rest, we can do some work. So one option is for a plus 5 to be equal to 0, in which case a is equal to negative 5. The other option, the other possibility is that, we'll do this one in hot pink, is that a plus 1 could be equal to 0, in which case a could be equal to negative 1. So the two solutions to our original equation were, let's see, negative 5 and negative 1. Those two numbers, when we substitute them in, will make that statement true. All right, how many more of these do we have? Let's see. Okay, 1, 2. Here we go. More equation solving. First things first, I see that we are not in standard form. Let's rewrite this in standard form. So we've got negative 3g to the 4th plus 75g squared equals 0. Now let's look for common factors. I think there's a common factor of 3, or even better, let's factor out a negative 3 so that our leading coefficient will be positive, but also g squared. So let's factor out a negative 3g squared now times the quantity of g squared minus 25. Oh yeah. Inside of our parentheses, I see we've got a binomial, and I'm thinking, hey, if it's a binomial, we're going to try and factor it as a difference of squares. Is this a difference of squares? Is this something squared minus something else squared? Absolutely. So that's going to factor, and it's going to factor very nicely as g plus 5 times the quantity of g minus 5. And so all of this equaling 0 means that one of three things must be the case. Either negative 3g squared is equal to 0, and the only way for that to be true is just g has to equal 0. It could also be the case that g plus 5 is equal to 0. And if g plus 5 is equal to 0, g's got to be equal to negative 5. Or it could be the case that g minus 5 could equal 0, in which case g would have to equal positive 5. So our original equation up here had three solutions: 0, negative 5, and positive 5. Crazy. All right. We continue. Holy cow, that is a big polynomial. It has 4 terms in it. It is in standard form, so that's nice. Are there any common factors? No common factors. Okay, so here we go. We are going to factor this, and with 4 terms, our only strategy is to factor by grouping. So let's go ahead and group these first 2 terms together. So 3w to the 3rd plus 4w squared plus negative 27w minus 36 equals 0. All right, common factor from the first grouping, I'm thinking just a w squared times the quantity of 3w plus 4. Common factor from the second grouping, I'm thinking negative 9. So negative 9 times the quantity of 3w plus 4. Awesome. I was hoping we'd get another 3w plus 4, which means we can factor all of this as w squared minus 9 times the quantity of 3w plus 4. And always, always ask yourself, can I factor more? In this case, the answer is yes. W squared factors even further. That's going to factor as w plus 3 times the quantity of w minus 3. And then, of course, we still got this 3w plus 4 going on. Holy cow. So, in order for this statement down here to be true, for all 3 of these to multiply to 0, either w plus 3 must be equal to 0, in which case w is equal to negative 3. Or it could be the case that w minus 3 is equal to 0, in which case w is equal to positive 3. Or it could be the case that 3w plus 4 is equal to 0, in which case 3w equals negative 4 and w equals negative 4/3. So 3 solutions to this original polynomial equation.